Welcome to our presentation on silt removal and the positive impact that it has on crop yields, water use efficiency, and irrigation system performance. A little background on me: I have an extensive experience going all the way back to the early 80s, but even farther back, and my father was one of the pioneers of drip, subsurface drip, so it goes back to the late 60s. But I've worked for most of the major irrigation manufacturers, Valmont, Lindsay, Netafim, developing areas for both pivots, mechanized irrigation, linears, as well as subsurface drip on crops like corn and soybeans, alfalfa, and other high value crops for surface drip. Without further ado, let's proceed. So in our presentation today, we're going to talk a little bit about what is silt and where does it come from, the impact on mechanical irrigation such as pivots and linears, the impact on low pressure irrigation, which is surface and subsurface drip, micro sprinklers and sprays, and this also applies to horticulture applications. We'll compare and contrast current solids removal solutions, sand separators, and hydrocyclones, and then we'll look at a new approach to solving this issue, how it works, and how it can improve the overall impact on the irrigation system performance, like longevity and improving water use efficiency, and improving crop revenues. And then finally, we'll open it up to questions. This is a couple pictures of the irrigation canals down in the Imperial Irrigation District. This is the main canal coming from the Colorado River. This is the sand dunes in Glamis, and you can expect during thunderstorms and other high wind events to see solids move into this canal. And obviously, if we look at this slide, you can see this is the natural color, and this is a lot of turbulence, and this is the suspended solids here that plague the irrigation systems on either side of this. And again, during wind events, you could see additional solids added to the canal. Here's another common source of silt and solids to an irrigation system. You can see the mountains in the background, and obviously during high rain events, we get runoff into this surface source. And you can see the high amount of solids that are in this water, as opposed to a lot lower amount during a normal course of business. Also, there's other events that occur, such as periodic cleaning of the canals. Of course, this one's unfilled, but here you can see they're cleaning here, and so that brings silt in. But you can also see that tremendous amount of silt builds up, and this washes down the canal, and you can pull it out in your irrigation system. So there are a lot of sources of silt, but it can occur in any number of circumstances. And so it's nice to protect your system if you know that your water source is a surface source and that it's exposed to corrosion and or wind-blown elements where you're going to get solids accumulate during the irrigation season. Another source of solids in irrigation water, particularly with open delivery systems, is runoff from fields. Typically, you'll have interceptor canals, or you'll go back to a canal downstream that may go to other farms, and you can obviously see the silt that's present in this water that either plagues current filter technology or can't be easily removed without settling basins or other types of overshot structures, and even those aren't 100% effective. If you're dealing with wells, whether it's submersible or turbines, a lot of times a new well will produce sand or silt, and so that it's nice to have protection and know that you're not going to have an issue there. Sometimes they don't settle out and they continue to produce. Other issues, like in West Texas and other parts where we have declining well levels, as they drop the pump lower to accommodate that, you start pulling out of areas where they don't have it gravel packed right, or you start pulling from areas that allow silt and solids to come through and plague your irrigation system, mainly your filters. And then, at these older wells, you've got well casing that might not be a plastic type that's finally corroded, and so it's letting in solids that also plague the irrigation systems. So let's take a look at what silt really is. It's a sediment, but we'll take a closer dive in so you get a real feeling for what we're really dealing with. So this is silt. This is what it looks like. And it's made up or comprised of bits of soil, rocks, sand, shells, remains of organisms. And it's finely ground. It's very small particles, about 10 times smaller than that of a sand particle. And it's got the same specific gravity, 2.6 to 2.9. And this is what plagues most irrigation systems, both the filters as well as the actual irrigation system itself. Sometimes it helps to look at things and compare it to real world things so we get an idea of the magnitude of difference in size. So if we look at sand, it's basically, and we took a 16-inch beach ball, and we compared it to silt, which is 10 times smaller. That'd be like holding a golf ball up next to one of those thin plastic beach balls. And then if we looked at clay as compared to silt, those are little beads your daughters or you may have seen on jewelry, and they're a 1/16 of an inch. So again, a factor of 100 times smaller than sand, which is basically 2 orders of magnitude smaller. And an order of magnitude is something times 10. And this you might ask your wife. She'll be able to tell you about these mineral type makeup. But you can see the particles in aggregate, but individually, when you wipe them on your hand or your face, they're not even visible because they're so small. So let's take a look at another way to compare silt and clay to real world items. So if I took your hair, we cut it the same length as the diameter, it's going to be 60 to 70 microns in size. So that gives you an idea. That's a pretty small piece. And if I were to take a white particle and lay it out on a black sheet, and we try to get one particle off so you could see, about as small as you can see is 40 microns. So anything that you can hold in your hand and see an individual particle, it's far bigger than 40 microns. 25 microns is about the size of a white blood cell. Cornstarch is probably a very good approximation of 25 microns. And then 8 microns is a red blood cell comprised by that black circle. And then 2 microns is a lot of the different bacteria. And I will tell you the average size of a virus is 0.35 microns or smaller. So we're dealing with very, very, very small things that you can typically only see under a microscope. So here's another look, and these are the things that we need to look at. So all the separators on the market today basically deal in this range, and this sort of gives you an idea of the sizes. And if you look at this in terms of millimeters, this is actually 1,000 to 2,000 microns. And as we go down and we look at very fine sand, it's from 106 to 150 microns. Very fine sand starts at around 53. There's some that say that that's also silt because sand really starts at 74 microns. And then from 2 to 50 microns is definitely silt in anybody's book. I use 2 to 74 microns. And then clay starts to be those solids that are, less than 2 microns. I usually use the 0.5 micron to 5 micron range for the clay. So let's discuss next the impact on mechanical irrigation, pivots and linears. There's a fair amount used across the United States and throughout the world. And even in California, we see some use of pivots and linears for some of the high value crops and some of the high desert areas. So what are the 2 areas that are mainly impacted by silt and sand in mechanical irrigation? And those areas are the system structure, particularly the inside of the pipe, which is also the support, and that'd be this area here, and then also the sprinkler packages, because even though this one doesn't show it, typically there's going to be a nozzle here and a pressure regulator, which we'll talk in more detail, and abrasion causes significant issues, as well as plugging for sprinklers. So I searched high and low for just descriptions of abrasion's impact on mechanical irrigation, and I can tell you from my discussions with people high up in the mechanical irrigation industry, they have seen a dramatic decrease in the life of the systems that typically lasted 20 to 30 years, as they've seen more sand and silt in the irrigation water due to declining well levels. And so the only place I could find it printed was in their new version, which actually is not that new because I was selling it 20 some odd years ago. But the poly-lined pivots and linears, they're not affected by abrasion from sand or sediment in irrigation water. And the majority of pivots use galvanizing inside and out, and therefore, as you abrade that, it's a sacrificial protection, and as you abrade it, you expose that carbon steel to the water and air in the water, and it starts rusting. Oftentimes in my discussion of how small a particle is, one of the comparisons I use is a chart and talk about those very small particles are very much like the particles that would be on emery paper. So let's look at the size difference. And you can see down here in ultra fine, I'm starting to look at 10 down to 3 microns, but even in extra fine, which you can go to the hardware store and check this out in terms of grit and ratings. But you can see here, and I don't know if this is upside down or right side up, but it doesn't matter. You can see that there's an abrasion of the entire surface, and that would be what I would expect. You can see some deposits of rust on the bottom, and you can see that as it worked through the protective coating, we started to get rusting. And this is basically a used pivot, but it's not had near as much abrasion. But even here you can see that there are issues with some sacrifice of the protective coating. Into the impact on mechanical irrigation in terms of the water application package. So here you can see I've got a pressure regulator followed by a spray, and these are all affected by solids in suspension, and it will basically abrade these and cause issues with fine particles getting into the pressure regulators, which can also cause problem with movement, and so you get a stuck regulator. And of course, as that water package starts to change in terms of its ability to control the pressure and the flow, you get a dramatic impact on your water distribution uniformity. And we'll take a closer look at that shortly. Now, these are old school nozzles for the original nozzles that came out probably in the 80s. And effectively, between sizes of nozzles, you've only got 1/64th of an inch. That's a very small size, maybe 100, 200 microns difference. In this case, it's about 400 microns. But then you split that in half because we're looking at the two sides. So now we're talking about 200 microns. So now you start to look at it. It doesn't take very much abrasion before I start to change my flow characteristics. When you have hundreds of nozzles out there on a machine, this difference in flow at the same pressure can have quite a dramatic impact in terms of your overwatering or underwatering on a pivot. So let's take a closer look at how pressure affects flow through an orifice. And most fields are not flat, so pressure regulators are a requirement so that we can maintain that design flow across the field and that high distribution uniformity that's promised by the mechanized irrigation industry. Note that if you have a pressure variation of 20%, you get a 10% flow variation. Now, this can occur because We've abraded the inside of the nozzle and the pressure regulator, but also you've got those very small particles that could easily migrate into areas that cause friction and sticking of pressure regulators, either open or closed or partially in either direction, that they affect not only the droplet size, but the radius of flow and the distribution of the pattern. So let's take a look here real quick. So if I'm at 6 psi and I have a 1 psi pressure change, or even a 5 psi pressure range, let's say it fails, you can see quite a dramatic change in terms of the capability of this pressure regulator to maintain flow. So what happens is now when I'm not able to maintain that flow because of these suspended abrasive materials that have compromised my regulators, now I end up in a situation where I either overwater or underwater, not just in one place, but all the way around the field or all the way down the length if it's a linear. So we'll look at that real close here in our next few slides. So when we look at the effect of the sprinkler package degradation due to solids either plugging or abrading or causing problems with the pressure regulators, you can see the amount of acreage that would be under each span in this. And of course on a linear it's going to be straight down the field. But now let's take a look here at this aerial photo that shows, look at this huge area here. I've got basically parts of 2 spans, and if we really look at it, the lion's share of that pivot acreage has been compromised due to either plugged emitters or we have problems with the regulators, and so we're not able to apply the full amount of water. And then if you look here, now we've got the other situation where we're overwatering, and this is a pretty good section of ground, maybe a couple acres. And then if you look at the outside area, I don't know if we've got a plugged gun or if we have problems with a pump, but there's a sizable amount of acres out here from this, either this overhang or this gun, and 3 or 4 acres, that's a lot of money when you're talking about a crop. So there are a lot of things going on here, but it's easy to see from this overhead that, this sprinkler is probably moving this direction, I would think. You could see where it was parked and not turned on. You could see here again something happened where it turned off. Here's something happened where it overwatered, and actually you can see the spoking in this field quite plain where they were getting overwatering along the whole line. And then of course you can see this span, there's something going on here because we're overwatering completely. Either the sprinkler drops have dropped off or the pressure regulators are stuck. And again, out here you can see that, although I'm getting plenty of water here, it's not quite reaching out to the edge of the field. So overwatering can be just as bad as underwatering because I've got other areas that are seeing a slight deficit. And it's also a waste of resources. And let's take a look here now at underwatering. And you can see there are vast areas that aren't getting enough water all the way along. You can see the wheel tracks where their sprinkler package isn't quite good enough. And of course you can see this pivot's probably moving this direction. And this is the watered area, and you can already see dry spots. But these are particularly egregious because all the way here it's underwatered. And then you can see here severe stress. They basically lost this crop here. Probably significant yield problems here. This is like 2 foot tall, whatever it is, corn, as opposed to 6 foot tall everywhere else. So again, here's another dramatic picture of what can happen if these regulators and sprinklers are impacted. So next we'll take a quick look at the impact on low pressure irrigation in terms of surface, subsurface drip, micro sprinklers and sprays, both the filtration and the actual irrigation systems themselves. So let's look at the normal size of filters provided in the irrigation world and compare that mesh versus microns, and this is 177 micron to 74 micron. And note this is all sand in this area as shown by this color code. And you'll see an example of the separator working in Kansas where they had an 80 mesh filter, which is basically 177 micron filter, and that basically was being overloaded every day. You can see for tapes we might have a 200 mesh filter, which would do the 74 micron. And so all of these solids below 74 micron are typically not addressed by filter systems or solutions offered by the industry. And so it's quite important what we're doing, because not only do these plague the filter, but they get through the filter and impact the system negatively. So from a high level, surface sealing in sand media filters is always an issue, and that seems to be the predominant choice for irrigation. But whether you're using screens, as we see here, or disc filters, if you've got a high load of sand and silt, not only will it damage some of these mechanical type filtrations significantly, but if you've got a high level of silt, it overloads the filters, as we'll see on, we'll take a deep dive into sand media filters, that leads to high frequency or continuous backwash or flushing, which means that your crop's not seeing that water. And that water is increased, and you've got to take it somewhere, either back to the ditch, or you've got to find some way to store it. And it affects your water use efficiency, which is the amount of water used per unit of crop produced. It also decreases your opportunity to irrigate the field. A lot of systems are, especially in the Midwest and in areas where it's supplemental irrigation, it decreases your opportunity to deliver water and nutrients to the crop. And so the overall loss of that water through the maintenance of the system decreases the water use efficiency of the total system. And then it has quality and yield impacts because we're not maximizing the full delivery capability of the irrigation system. So let's look at this a little bit. So let's look at this in reference to a sand media filter. And typically you bring the water in from above in a manifold. It comes down across the media, goes through the filter media and through the under drain and out to your system. So let's look at this jar test here where we have a sand layer, a silt layer, and a clay layer. And first point I want to make here is this media in the media tank is the same specific gravity of any sand that might be coming in. So if you have a sand issue, you definitely should have some type of pre-filtration to stop that sand from coming in, because it mixes or infiltrates with the bed. It's very difficult to backflush this out, and actually you'll backflush a lot of your filter media just to get that out. But let's look at it in context after that caution of this is our media bed. I've got a layer of silt and a layer of clay, and often it's going to be a very thin layer of silt and clay before this thing completely blinds off. And that's what they're showing you here is this fine sand, not even silt makes it worse, has now created what is known as a dead area. And so this water tries to move the sand out of the way so it can get through. Over time, in many irrigations, these dead areas tend to grow. And so this problem becomes more egregious till, in some cases, in the worst case, it actually moves all the sand away and flows right through that under drain. So it's very important that we remove these silts and clays because they're very difficult to remove with backflushing, and they're the same specific gravity as sand, sometimes a little bit heavier. In addition to the effects that silt has on filters, you saw just in the previous slide the effect of surface sealing on a media filter. Those same things happen to disc filters as well as screen filters, and a little later on we'll see an example where they had an eddy mesh screen that was basically being overwhelmed every day by silt. And so the size difference between those two is huge, but there was so much that it plugged the filter. And so that had a dramatic impact on not only the filter, but also the drip lines were filling up, which we'll talk about shortly. But how does it affect, mini sprays, mini sprinklers that are common in the industry? So again, these nozzles are a lot smaller. You're looking sometimes 121 over 128th of an inch difference in nozzle sizing. Your everything is smaller. A lot of them have moving parts in them that are subject to wear and tear. So nozzle wear and tear on the motors can be an issue. Plugging, especially with silt, can be an issue because everything is a lot smaller. What happens is now I've decreased water and nutrients to the crop, and you might not see it till the end of the year. And so that has a dramatic impact because these are very high value crops. So just a slight yield decrease or not reaching, optimum yields can have quite a financial impact on the grower. And of course, it affects a decreases the water use efficiency because I really didn't get my full amount of water and nutrients, which is what are needed to optimize the crop produced. And then that also may have quality impacts. If you've got an area that's a little lighter irrigated, you might have sizing issues or even quality with the fruit. And then in the lines themselves and in the sprinklers, now that I've got silt in there, that acts actually as a food source. And a lot of biologicals use it not only to grow, but it also becomes an environment for them to proliferate. Whether you've got button drippers or inline drippers for surface or subsurface drip, if you've got silt getting into your system through the filters, then you've got the issue of partial blocking or even complete blocking of the emitter. And again, this decreases the water and nutrients to the crop, and it's probably even more of an issue because you can't see what's happening if it's below ground. And so now I'm impacted by this decreased water use efficiency because I haven't provided the optimum water and nutrient for the crop to be optimized. And then, of course, again, we could have quality impacts. If you've got an area that's lightly irrigated or over irrigated, it causes disease issues, could impact your crop quality, could impact insects, a whole slew of different items that could be impacted that affect the bottom line of the grower. And then, of course, within the line itself, now not only do I have silt issues, but now I've got increased biological action, which means I've got to do more flushing, and that's probably the biggest thing is the flushing and the impact on your system. It's very hard because these things are buried, so it's a lot of them in a surface situation, so it compounds the maintenance issues. I think this next video is very important, and this basically shows they don't have a flush manifold on this, so they have plugs on the end of each line. But this basically shows the amount of silt and other material that got through the filter into the system. And you can imagine that this is not only in the pipeline, but it's also, or the tube, but it's also in the emitters and in the sprays or the mini sprays that they might have in that system. And it also creates an environment for those solids to be, or for biologicals to grow, and they have a food source. And so it really impacts the life of the system. It impacts the distribution uniformity, the water use efficiency. And in fact, one of the case studies you're going to see a little bit later on, the guy was flushing his zones every single day. And that was a tremendous amount of time, effort, and water lost. So next we'll compare and contrast current solids removal solutions to a new solution that we're going to learn more about later on in this presentation. So these are the two basic main solutions that are available in the marketplace today. This is a simple hydrocyclone. The water comes in, it gets spun around, the solids fall to the bottom, and the clean water comes out the top. This is a separator, and the only difference is this is a cone, this is a tube. Comes in, gets spun up, goes through slots if it's a case of this manufacturer. Some of them don't even have slots. And basically we spin up the water, the solids fall out, and the clean water comes out the top. the previous two separation technologies that you saw only provide removal up to or down to 74 micron reliably. So this is a new approach that will remove clay, silt, as well as the sand. And so it's quite a new breakthrough. It operates over a wide flow range, where those other two technologies, you have a sweet spot for it. Anything outside that dramatically impacts either the pressure loss or the ability for that to move solids. And this can be manifolded, as we'll see, to provide higher flow rates. And if we use this in a prefiltration, not only do we, or as a primary filtration, do we remove those solids to protect the filter, but also the system. And so we might see at least a 5-time decrease in high solids loading of the filter backwash. Now, here is a recent installation, and these are all 2 or 3 inch hydrocyclones. Notice the diameter across here is quite large. This is galvanizing, so they're going to have rust and abrasion issues, and eventually these are going to fail, probably within about 5 years or less. And you'll also notice that they're not center fed, so now some of these separators are going to see more solids than others. But the bottom line is, I was doing this 20 years ago, and yet the market is just cottoning on to using smaller separators in lieu of one large one, as you'll see in the next slide. So here's a picture of one of the people I used to work for, both companies actually. This is a centrifugal separator. Again, remember we had the tube in here. It's somewhat smaller than this diameter, but larger than this diameter. And we'll be lucky if we get 74 micron, and I can tell you a few of these came back. But it was used as a primary filter to protect this pivot corner from, which is installed with subsurface drip, from plugging up the system. But I can guarantee you, if there's any silts, they're getting right through that, and they're impacting this system. And I can tell you, they don't put flush manifolds, so they have to go out to every one of these lines at the edge of the circle and flush it manually. And it's quite a pain in the butt. Now, let's look at the application. How we would address it, and you'll see more detail. But center fed, basically each individual unit is in parallel, commonly flushed. And so this is a very good installation, and it worked quite well. Let's take a quick look at separators. Whether they're hydrocyclones or centrifugal separators, they're most effective in removing inorganic particles and solids with specific gravity significantly greater than 1.2. Current separator and hydrocyclone offerings basically offer working pressures in the 12 to 22 psi differential. In other words, that's a pressure loss to get any separation, and they require those pressures to be pretty spot on. Their sweet spot for actually doing what they advertise is very small, whereas our separator will work across 1 to 15 psi loss for a very efficient separation. Typical removal efficiency, and I went out and found all the literature, is no more than 74 micron. Whereas when you look at our stuff, we're looking at high removal efficiencies down to 5 microns and pretty significant removals down to half micron. If we do a jar test, which is typical in the industry, you take a sample of the irrigation water and you put it in a clear container, you shake it up. Whatever settles out in 3 minutes is what they expect that separator to remove. When you do our jar test, it's 24 hours, and that shows the typical solids removed, and I'll have a picture of that here shortly. Another problem is that these centrifugal separators require 20 psi minimum inlet to operate, and the hydrocyclones are pretty much the same. And that's 20 psi for the inlet. If you have 12, you only have 8 left. So the bottom line is you've got to have this much above the 20 if you need that pressure downstream. So these tend to be use a lot of energy, and people resist using them because of that fact. Whereas with ours, the minimum inlet pressure is 10 psi, and we've even got some operating down as low as 8. So let's look at and how we've approached solving the issue of silt and sand in the system and how it works.
And then we have solid separation technology that provides down to half micron removal and takes like 66% of 5 micron down in a single pass. And those can operate as low as 1 to 3 psi differential. Basically, we provide very low water loss solutions, and they all run at the lowest energy levels. In other words, the lowest pressure losses of any equipment in the industry.
As you'll see here, we've won 2 awards in the last year. One from the Irrigation Association as the top product for last year, and the top 10 innovative winner from Bank of America at the Tulare Farm Show, which, if you're watching this, you're attending this year. So let's start how this separator works by the water movement through the separator. So the water comes in from the bottom, gets distributed to 16 radially placed 1-inch hydrocyclones. The water enters each of those hydrocyclones, is spun up, the solids are moved to the outside, gravity becomes a predominant force, they fall down into the collection chamber. The clean water comes out through the center of the vortex and out to the system. The collected solids are periodically purged through this port here, and we can tie those ports together. Usually I don't tie any more than 4 at a time with automatic purge, and we highly recommend it. So let's take a closer look at how our separator works so well and why we came to the conclusion that 16 separators would work better than one bigger separator. So first, let's talk about angular velocity, which is the speed or the velocity around this circle if I had something moving there. And it's defined as velocity over radius. And radius is nothing more than from the center to the outside. Now, a good real-world analogy of this would be if I had an ice skater who entered a spin with his arms outstretched, or her outstretched arms, and the radius would be from the center point of the person to the tip of their finger. Okay, and so you can see that we'll get it's fast, but it's not very fast rotation. Now, we thought about, well, how do we get faster rotation in the same footprint? So, okay, what do we do in this footprint to get that faster rotation? Well, what if we went to smaller, somehow combined or manifolded separators? So, if we look at the same situation where I want to look at what does decreasing the radius do for me, think about again about our ice skater. Now the radius is from here to here, so that's just like the ice skater pulling their arms in and they rotate faster. Okay, so if we think about that, and let's change it to a dot, and let's show that solids moving around the outside. Here is the speed in the current offering, and basically we could separate a 74 micron particle or 200 mesh particle. But now if I do the same thing, look at how fast I'm able to move a smaller particle and separate smaller and lighter particles. So we've established that a smaller diameter or smaller radius will give us a higher velocity. And so we looked at, okay, what if we take that and expand it out? What's a good size? And so we came up with a 16 hydrocyclone separator. And basically you can see now I have 16 of these working just as hard. I have just the same flow rate as in the other footprint, but 1/16 of the size of the hydrocyclone for a 2-inch. And so now we're able to claim quite dramatic capabilities. Real world. Well, as we discussed, we have our simple sample, which was agitated, and we basically look at this and say, oh God, there's a lot of silt in there and sand. And a typical centrifugal separator or hydrocyclone offering in the marketplace would use a 3-minute settling test. And you can see we got a significant amount of sand, but there's a lot of solids that were very close to that video that we saw with the solids coming out of the drip tube. And then if you look at our sample, we agitate it, and this was based on the video that you'll see, but 24 hours of settling time, and you can see not only did I get the sand that we got down there, but I got a thin layer of silt and clay. Actually, there's 3 or 4 layers here. So dramatic improvement in terms of the efficiency of removal of solids by this separator. So when you look at this picture here, this is a paste, this is silt. This is what we actually removed from this well, which you'll see shortly. But also, that jar test that you saw preceding, we did the same thing on this one, and it took 24 hours for all these solids to settle out and approach the clarity of the water that exits in this video. So without further ado, let's go ahead and look at the video. So here's the purge. The water comes into the bottom of the separator. Okay. You can see there's a lot of silt here. The water comes in from the bottom, goes up through the top and out. Now we're showing continuous purge here because we want to do the compare and contrast. Now this is operating at about 1 psi differential. We have a automatic valve here. Now he's backed the pressure off to 3 psi across this in terms of loss. And so now we're getting adequate flushing. He's taking a sample of those purge water. We'll end up taking a sample of this clear water. And that's actually what we use for our standards. This is done about 18 months ago in the field. Now this particular grower had an 80 mesh filter that was having 1 or 2 flush requirements a day. It was a manual system. And when he put this on, he was going over 30 days between flushes. And he was dragging drip tube behind his pivot, and that no longer needed, daily flushings or weekly flushings or bi-weekly flushings as the situation dictated. So that then all of a sudden they weren't having to go down and take 1,000 lines and clean those out either. So I want to talk briefly about how we actually determine the efficacy of removal for the separator. This was actually tested. We had an agitated supply of the solids. We had a hydrocyclone. There was a sand media filter in here that was ostensibly to test how well this would increase the frequency between backwashes on this filter. And so that was our test system setup. So let me quickly go over our test media that we used in that test setup. 100% of it was 80 micron and below. And I can tell you, with my experience at a previous centrifugal separator manufacturer, that maybe 10% of our sample was 74 micron and above, and then the majority of it was 120, 150, 200 micron particles. So not even testing it with this kind of solids. So here's the results of our test, and you can see that there are buckets 50 to 80, 30 to 50, 15 to 30, 5 to 15, 1 to 5, and 0.5 to 1. And these are in microns. So let's just look at the 50, 30, 15, 5, so on. Now, for 50 and above, 99%. Definitely do as good as the rest of the guys, but I can tell you that they're not going to be anywhere close to 99% on 50, 60, or even 74 micron. 30 to 50, again, 30 micron above, we're at 99, okay? And even if we look at 15 micron, which if I remind you is far smaller than a white blood cell, we're getting 94% removal in a single pass. And at 5 microns, 66%. This is the majority of the silt that plagues the system, and we can take most of that out. Here we've got 2 levels of clay, and the bottom line is that these solids here should be higher, but they broke up, and so a significant higher amount ended up being captured in this particular portion. Now, here's the sand. These are silt. This is clay. So you can see that in this area here, we're doing stuff that the others can't even begin to touch. So let's look at the positive impact on irrigation systems. Remember I showed this test system and the sand media filter. Well, this next slide will show you the effect and the improvement in the operation of this media filter in high solids loading conditions with a hydrocyclone as the first stage. So let's briefly look at how well the CPH16 can improve system performance when it's used in front of another filter type, in this case a media filter. So on this axis, the primary y-axis, we have PSI and pounds. On this axis, we have gallons per minute, and on this axis, we have minutes. The dashed lines represent the data sets for the test without the CPH16 as the first stage, and the solid lines are the data set for the test with a CPH16 upstream of a media filter. The blue lines are graphed the time against this axis, which is gallons per minute. The yellow and brown are basically against this axis, the yellow for the PSI for the differential pressure, and the brown for the dust that we injected. So we go along here. This is the differential pressure in our first test, and somewhere just past 30 minutes, we start to see an asymptotic rise to what would ostensibly be a requirement for flush, although they let it run longer to see what was going to happen. You can see we injected about 2 pounds of dust, and our flow rate dramatically started to decrease at the same time that our differential pressure decreased or increased. And so you can see here we got all the way down to almost 50 gallons a minute from 65. Now, we reset the system, reran the test. Now the solid lines are with the CPH16 upstream. You can see at this point here where we normally would have had a backflush commanded that we were still pretty flat. We saw some increase, but this is a pretty dramatic injection of solids when you think we're only going 65 gallons a minute, and this is 9 pounds of solids. So we ran out of solids at 9 pounds, but you can see based on a linear regression that I did with the thin lines, that we would have crossed the threshold and required an irrigation at slightly over 150 minutes. This is 120 minutes longer than the system without the CPH16 would have run. And in fact, it tells us that, from here to here, we can run 5 times longer. I would expect that to even be a higher differential in terms of time and between flushings with lighter solids loading. But this is pretty egregious, so this is a very good example of what we could do. The next few slides basically show what we could do if the only thing that was required were separators, because we had no organic material, just silt and sand. And so this one would go from 800 to 3,000 gallons a minute, 3 psi loss if we didn't really have the pressure to burn, or 15 psi if space was a limitation. Here's a smaller system that would go from 600 to 1,500 gallons a minute, again with that 3 to 15 psi loss across the filters. And you're looking at 3 feet here and about 10 feet total from here to here. So this is a pretty compact system. And of course, we can add, because everything is set up like Legos, we can add as many of these as we want onto the system. This shows the system basically with a prefiltration, as we saw in the test, upstream of the media filters, and you can see this would handle 1,600 gallons a minute, and we're in a pretty small space of approximately 20 feet. So this is quite impressive in terms of most media filters would take up more room than this, and we only have to backwash 50 gallons a minute out of these tanks versus 250 gallons a minute. Screen filters, or have set up their flush water to basically flush to a reservoir, and we've found a way, and we've actually tested it. But in this situation, I've only got media filters. We could have separators upstream, which would really help out this part of it. But we take all of the backwash water off of this, we run it through a gravity screen filter, and we pump that through a separator. And since these filters only require 50 gallons a minute, and each one will handle 100 gallons a minute for filtering and 50 gallons a minute for backwash, we're able to handle it with a single separator. We have a smaller version, so we can take the solids out, we can take the organic material out, and we could return this water. This will save about 98% of the water you would normally lose through a backflush operation, because the purge from this and this are quite small. This just shows a graphic representation of a system that would provide that 98% water savings, along with the ability to handle 1,600 gallons a minute. And we could have separators upstream, which would reduce the backwash requirement even less frequent. Here's a very short video on a case study that we did that showed the efficacy of this on a recycling system.
Or big pieces of matter that we couldn't get out and we're plugging up our filter systems. So what we did is we installed 2 large screen filters to try and block some of the bigger pieces of algae as well as some of the bigger pieces of organic matter. We then go into our sand media filters. That still didn't quite clear it up, so we added a gravity filter. We were still getting some very fine material coming through here that was plugging up our sand media filters. So we added the Epiphene filters here. We noticed right away that we were able to flush multiple times without having that issue of plugging up. So it's better quality into the field. We're not wasting any water. Basically just getting the cleanest system we can, so that way we're efficient with energy usage and all of that good stuff.
So typically, this is a summary slide of an economic model that we built for side-by-side comparison of a number of different factors in terms of media filtration, solids protection, and the operation of the system. And we're available for Zoom meetings and or site visits, but this shows the savings over 30 years with just the separators. This shows it with just the separators and also lifetime media. And you can see that regardless of where we look at, it's quite a bit of monies. The water savings, which was quite impressive, was 19,600,000 gallons over a 30-year period, which is equivalent to 60 acre-feet. So quite an impressive amount that could have been either left in the aquifer or delivered on the crop for increased yield over all those years. In the previous model we looked at, we saved about 2 acre-feet of water, which could have been spread over the entire field. And of course, this model doesn't account for improvements in yield and quality by decreasing the times you have to flush, the impact on the reduced water to the field during those time periods when you might have to use a PSNO valve or something similar. But we thought a rough approximation of what you could save or improve in your operation might be interesting. In this case, we use corn, but you could use tomatoes, you could use, more high-value crops. But, we were looking at, an additional $750 per year for that field, which would have been another $22,500 in uninflation adjusted costs. So this is a summary that included the yield information that we covered on the previous slide, and this went from 217 to 270 based on the yield over 30 years with inflation, and with a lifetime media went from 242 to 348, which was quite a big savings. And of course, overall, the savings between these two options, non-lifetime media versus lifetime media, was $77,000. So when you look at this water savings, the model didn't include this in terms of what is the value of this water still in the aquifer 30 years from now, or had it been applied over the field or another crop during this 30-year period, what would have been the value that would have added to the total accumulated dollars. Let's quickly discuss a summary of what we learned today. So today we learned about what is silt, where it comes from, impacts on mechanical irrigation, impacts on low pressure irrigation. We compare and contrasted current solids removal solutions to our new approach to solving the issue and how it works and how it positively impacts all factors of the irrigation system, and the potential impact on water use efficiency and crop revenue by improving the filtration system and or the water package delivery system. and protecting it. And then, of course, we left it open for questions. But because of the time, we would ask you to send your questions to info@epiphene.com or visit epiphene.com and send questions via our contact form. We're hopeful that today was instrumental in providing you a foundation for future considerations for your irrigation system, either new or in a retrofit basis, and improving your overall production capabilities. And we thank you for your time.